Right, so just for this, sorry to repeat myself, but just for the sake of making it into the recording, like I said, in our discussion of nucleic acids, as in all of the biochem chapters that we have, there's about 4 of them, my focus is not going to be in biological function. My focus is mainly going to be on structure, which is what we've been focusing on all term. I think by now you guys have gotten the idea that we organic chemists are quite obsessed with structure and understanding the structure at the molecular level of various compounds and species. And so I think if I do my job well, you'll see that although nucleic acids are very, very large molecules, they're understandable in terms of some things that we've talked about already. The only thing that might be a little bit new is the ribose portion, or deoxyribose, the sugar portion. And we'll have more to say about sugars later. We also do have a chapter in carbohydrates, but I'll kind of be presenting that as its own separate thing. And that's really what I'm going to do here today, is kind of build up nucleic acids from the bottom and go over all their parts and then show you how they're put together to make a simple, let's say, dinucleotide. Even though your exam will still be multiple choice, I would expect that, at least given the structures of the nitrogen bases, which again, I don't expect you to memorize, you would be able to draw a simple trinucleotide, given enough information, you know, without, like I said, certainly not memorizing the nitrogen bases, but given enough information. And we'll end with a couple of examples of that, I think. So first of all, the so-called nitrogen bases themselves. These are nothing more than derivatives of purine and pyrimidine. And we've gone over purine and pyrimidine just recently in the chapter on heterocycles. So we know that purine is a heterocycle consisting of 2 rings, a 5-membered ring and a 6-membered ring fused on one side with a total of 4 nitrogens. So that's purine. Pyrimidine is also one of the so-called diazines that we went over, meaning it's a 6-membered ring with 2 nitrogens, and other than that, isoelectronic with benzene. So the way I remember these, by the way, it's kind of a dumb mnemonic, and I would not be shocked if you can come up with a better mnemonic. But the way I remember which is purine and which is pyrimidine, and thus also which are the 2 purines and which are the 3 pyrimidines, the way I remember that is the length of the name doesn't go with the size of the molecule. So purine is the smaller word, but it goes with the bigger heterocycle. And pyrimidine is the bigger word, but it goes with the smaller heterocycle. That's how I remember. So you're welcome to that if you find that helpful. But like I said, I'm confident you can do better than that in terms of coming up with a mnemonic device. Now, in terms of, and again, I don't want to focus on biological function, but in terms of where you find these heterocycles, of course, both purines you will find in both DNA and RNA. They are involved in both types of nucleic acids. And as for the pyrimidines, cytosine you will find in both DNA and RNA. And then I bet you even learned in your high school biology class that thymine you find only in DNA and uracil you find only in RNA. The difference between the two is just this one methyl group. In uracil, that's not a methyl group, that's just a hydrogen. But other than that, the structures are identical. One thing I should probably emphasize in terms of just the structure of the nitrogen bases, actually, before I get into the structure of the nitrogen bases, before I forget, why are they called nitrogen bases? This is something I didn't find out until many years later. They didn't tell us in our biology and biochem classes. But they're called nitrogen bases because they really are bases. They've got alkaline nitrogen atoms in them that can be used to abstract a proton from a strong enough acid. And the same is true of purine and pyrimidine themselves, by the way. So they're called nitrogen bases because they're bases. They have amine nitrogens in them. And so they can act as bases just like purine and pyrimidine can. In fact, in purine, it turns out to be this nitrogen over here that's especially alkaline. It's even a little bit more alkaline than pyridine. And in pyrimidine, I would say they're equally alkaline. They're pretty much equivalent nitrogens. So that's why they're called nitrogen bases. Otherwise, in terms of the structure, I think you'll see the clear analogies between adenine and purine. I think they're almost the same, except for one more amino group in adenine. But guanine looks a little different at first blush. And the same can be said of cytosine, thymine, and uracil. They don't seem to have quite as many double bonds in the six-membered ring as pyrimidine does. And there's actually an explanation for that. Let me see if I can make my whiteboard a little bit smaller, because I want to still be able to refer to these structures. And then we'll go on the whiteboard. That wasn't as I intended. There we go. That's more better. So there's an explanation for that, though. And let's just look at the structure of cytosine for just a moment. Let's see, we got a nitrogen over here. And you can see for yourself, I don't have these things memorized. I know in general sort of what they look like, but I don't have them memorized. There we go. So there's cytosine. Cytosine has another resonance form, which looks quite a bit more like pyrimidine. And that's what's known as the enol form. And that looks like this. There's now a plus charge on this nitrogen. Wait a minute, what about NH? I'm sorry, I forgot my H's. Shame on me. I had nitrogens with only 6 electrons around them. There we go, that's better. So now that's got a plus charge, this still has a lone pair, and the rest of the electrons go in just as before. Oops, what about the octet? Oh no, we're fine. We've got an octet around oxygen. Good, we've got all our lone pairs in, good. So cytosine has another resonance form that looks like this, and that I think you'll agree looks quite a bit more like pyrimidine. Pyrimidine just is like this. And so now it looks quite a lot more analogous. As it turns out, though, this resonance form doesn't account for much of the overall structure, because it turns out that what's really critically important in these nitrogen bases is hydrogen bonding. And so this electron configuration is much more efficient, or much more capable at accepting hydrogen bonds, than that one is. So even though this does account for a small portion of the overall structure of cytosine, what we find is the structure is really better described by this type of structure. So again, that's just for the purposes, I think you're already aware of nucleic acids involving hydrogen bonding. That's the so-called rungs of the ladder, are hydrogen bonds between the different, the two strands of either DNA or RNA. And so they need to be effective at hydrogen bonding, both in terms of donating and accepting hydrogen bonds. So that's why. I just thought I'd point that out, because at first glance, when you look at these structures over here, they're like, it doesn't look all that similar. Well, there is a little bit of that structure in the description of the compound, but really this is the one that's more important in terms of the chemical behavior. So I just thought I'd explain that. Let me make sure I'm not forgetting anything else. Right, it says you don't have to memorize the structures of nitrogen bases. These types of structures show up a lot, by the way. If you look up the structure of caffeine, well, heck, we certainly have time today. Let's do that. I don't know the structure of caffeine, not off the top of my head. I really should probably, well, wait a minute. Will this take me to, I don't want to share it. Caffeine structure. There we go. Indeed, it does look very purine-like. In fact, it's another purine. So I think this structure is clearer. So we'll maybe go with that one. Yes, you need to know that for the exam. Kidding, I'm just kidding. You don't have to memorize the structure of caffeine. But I think you can see that wants to induct me into its set of web information. But be that as it may, I'm only kidding around. But you can see this is also a purine, just like the two purine bases. So anyway, thought you might find that interesting. I think we all use caffeine on a somewhat regular basis. Good. So I think that's all I need to say about that. One thing I'm not entirely happy about in most organic textbooks, yours is less bad than a lot that I've seen, but they don't make the distinction clear enough between nucleosides and nucleotides. And I want to be sure that we make that distinction. So nucleosides involve the nitrogen bases and also a molecule of either ribose or deoxyribose. So let's draw ribose in here. Why am I absolutely blanking out on ribose? Which I kind of do have memorized, but that's an H over here. Oh, here we go. Okay. Whew. I don't expect you to memorize it, but I do expect me to memorize it. You know what? Let me do that all over again and do it bigger. I'm trying to learn how to draw bigger. Make it easier to see. So they use this kind of strange three-dimensional type of drawing for sugars rather typically. These are called Hayworth projections. Not that I really care if you know that. Over here we have H and R, and then OH again up here, and hydrogen over here. This structure is, when R is OH, that compound is ribose. I don't think I really care if you memorize the structure of ribose either, but I would like you to be able to recognize it and know where it goes in the structure. And when R is H, you've got 2 deoxyribose. Deoxy meaning exactly what it sounds like. We take away the oxy. There's 1 fewer oxygen. So instead of OH, it's just H in deoxyribose. And as you might guess from the names beginning with R and D, those are what you will find respectively in RNA and in DNA. So that's where these structures show up. And in order to make a nucleoside, we need to combine the ribose or deoxyribose with one of these nitrogen bases over here. And they must be combined in a particular certain way. And so certainly we will go over that, but that's what we'll get to next. But I've already defined nucleosides. I just want to show you where. I've defined nucleosides in your class notes. It's an NO-acetal, and we're going to define that also when we actually draw the structure. We're going to define it using a picture. But it's a functional group called an NO-acetal with one of these nitrogen bases with either ribose or deoxyribose, depending on whether it's the type of nucleoside you'd find in RNA or the type of nucleoside you'd find in DNA. So, let's start by drawing a nucleoside or two. So we're going to start, actually, it doesn't matter what you start with, but I'm going to start by drawing my ribose. And maybe I'll make this ribose so that it has an OH over here. And then up here, instead of the OH group, we're going to replace that with one of the nitrogens in the nitrogen base. And maybe I'll do one of each type. Let me just for fun put an adenine in here. In adenine, it's going to be this nitrogen over here that gets involved. And it would be similar for guanine. We need a double bond over here. We have a double bond over here, and we have a double bond over there. So I think that's all we need. So this is, over here we've got adenine. And this is going to be an RNA type of nucleoside, because we have that OH over here. So you see, this is how they're put together. And like I said, these sort of, they have peculiar bond angles, don't they? The way they draw these rings as though you're kind of looking at it edge on. Sometimes, if you want to be fancy about it, you can maybe darken these lines, so make them bold, so it looks like they're in front. That looks kind of cool. But I consider that thoroughly optional. But if that makes you happy to do that, go right ahead. Might make it a little easier to see what's going on there. So, so this is a typical nucleoside. It has the nitrogen base in what's called an NO-acetal. And what makes it an NO-acetal is this carbon right here. An acetal is a carbon that's bonded to single bonded to two oxygens, or has two single bonds to oxygen. That type of compound we generally call an acetal. What makes this an NO-acetal is instead of two oxygens, it's an oxygen and a nitrogen. So that's what we mean by an NO-acetal. That's the definition of that functional group. It's just another functional group, not one we run into every day, but it's another functional group. And that's also what makes it a nucleoside, is having that NO-acetal and involving the nitrogen base, and I'll draw another one too, so you can see how this works, and either ribose or 2-deoxyribose. That's what makes it a nucleoside. Let's do one more. Maybe I'll make a DNA type one. CH2OH. And let's put both H's over here so that we can see its DNA type. And which nitrogen base do you like? Let's do thymine, since we find thymine in DNA. Then it's going to be this nitrogen here on the bottom. And you'll notice, of course, I took away the hydrogens from those nitrogens, right? So that I can form the bond to carbon. There's that methyl group, that all-important methyl group that makes it thymine. And I believe that's it. So this is thymine over here. And this is going to be a DNA type nucleoside. So like I said, my goal is for you to come out of this understanding the structure of these things and how they're put together. Not so much memorizing everything, but being able to make sense of these structures. And although this, even before we get into nucleotides, let alone polynucleotides, even already for us, this is a pretty darn big molecule. But my point is we can understand it. It's going to be a ribose, which now is a thing we know. And it's going to involve one of these nitrogen bases. That is how single nucleosides are put together. Good. Any questions so far then? Yes. Oh, well, there's any number of, I mean, I don't want to give them all away, but well, that wouldn't make a very good multiple choice question because there's only two possibilities, but sure, something like that. I could ask you about how the two are connected, you know, that might make a slightly better question, but I could, we could talk about how many carbons are in ribose. I don't know. There's any number of questions that can come from this. That's actually a really good thing to do to practice for exams, is make up your own multiple choice questions. I don't mean you personally, I mean all y'all. No, I don't expect you to memorize the nitrogen bases. I won't go like, which of the following is adenine? No way, because I don't have them memorized. So I wouldn't do that to you. I mean, if you want me to put an upper limit on it, I guess if you guys knew that adenine and guanine were the purines, that would make me happy. And if you knew that these other three are the pyrimidines, that would make me happy. And certainly we already know about purine and pyrimidine from chapter 13. So that'd be really good. But no, I would not say, which nitrogen base is this? No way. I would never do that to you. Question 1, which nitrogen base? I'm kidding, I'm just kidding. Jeez. Okay, so with that, I think we're ready to go on to nucleotides. And again, that one letter change from an S to a T makes kind of a difference. So nucleotides are like nucleosides, except they also have a phosphate ester, either a monophosphate, diphosphate, or triphosphate ester. And that ester can be at the so-called 3' or 5' oxygen. That's another thing I really wanted to explain, because I bet you heard them talking that way in your biology classes, the 3' oxygen, the 5' oxygen. They never explain why they do that. But those prime numbers are used in the ribose ring. 1' is over here, 2' over here, 3' this carbon here, 4' over here, and the 5' carbon is this one over here. But the reason they put the primes on is because the nitrogen bases themselves also have a numbering system to the heterocycles. I don't expect you to know them, but all of those atoms also have numbers, 1, 2, 3, 4, 5, whatever. And so they need to put the primes in order to draw attention to them that they're talking about the ribose ring, not the ring of the nitrogen base. So that's why they do that. That's another thing I didn't find out until 15, 20 years later. Finally, I found that out. They didn't mention that in the biology classes. And again, I know I'm kind of biased. I don't mean for this to be coming down in biologists. They have a different focal point, you know. But that's maybe where I can come in and actually do some good, maybe. Because otherwise, I don't think it's intuitively obvious where are these primes coming from and why. So that's why they do it. They're doing it to make sure that you understand they're referring to the carbons in the ribose ring, not the atoms in the nitrogen base ring. Good. So let's get into some nucleotides then. I defined nucleotide over here. It's a phosphate ester. First of all, we need to understand what phosphate esters are. First, I have to get the element right. This is going to be a monophosphate ester. A diphosphate would have 2 of those in it. It's again another functional group, not one you run into very often. I'm only putting lone pairs on the oxygens that have a non-zero formal charge. The others will all have 2 bonds and 2 lone pairs. That's a diphosphate. And you can probably guess already what a triphosphate will look like. Let me see if I can fit it in. Barely. You'll notice also that the phosphorus atoms in phosphate esters are hypervalent. So how many electrons do we have around this phosphorus? 2, 4, 6, 8, 10. So again, that's allowed. You can have more than 8 electrons around any element that's in the 3rd row of the periodic table or below. But remember, in the 2nd row, like for nitrogen, this can never, ever happen. Those elements never, ever violate the octet rule. But in the 3rd row and below, it's allowed for them to violate the octet rule. They don't have to. Phosphorus can also just have 3 bonds in 1 lone pair, like an amino nitrogen. That's allowed too. But phosphorus is able to take on more than 8 electrons. And maybe I'll comment on that too. Something I actually learned only about 5 years ago, which was that I was lying to my students for years when I taught Gen Chem. And your Gen Chem professor might have said this also, and unknowingly have lied to you. What I always told my students when I taught Gen Chem was the reason that elements like phosphorus and sulfur and so on can take on more than 8 electrons is because of the orbitals in the 3D subshell, that those 3D orbitals are empty and they're able to take on extra electron density. And it's very plausible, and it certainly matches with what we see experimentally. The trouble is, more recent calculations have shown that the d orbitals really aren't involved in this phenomenon. So it might have something more to do with atomic size and or electronegativity. That could be involved also, but my entire previous part of my career at my previous school, that's what I always told my students, and it turns out not to be true. So there you go. This is a triphosphate. So what we're going to do is make a phosphate ester, one of these three types, either monophosphate, diphosphate, or triphosphate. And we're going to put that on either the 3' oxygen or the 5' oxygen. And that's when you will have a nucleotide rather than a nucleoside. So let's draw a nucleotide using, I don't know, what nitrogen base do you like? Uracil, you like uracil. Well, if we do uracil, then it'll have to be RNA type, won't it? So we'll use uracil with a diphosphate at the 5' carbon or 5' oxygen. So what we'll do, since my 5' carbon is over here, let me just sketch in my ribose ring. Instead of writing CH2OH, I'm going to put my diphosphate ester over here. So there you go. That's my diphosphate ester. And since we know this is RNA type, these had better both be OHs. It's not deoxy. And then over here, we'll put our uracil, which I will have to look at, since I said I don't have them memorized. And I certainly don't expect you to either. And then just a carbonyl in between. So you see these molecules are getting bigger, but I think it's still something that we can understand based on the parts. And the only thing we need to add to this, and I might just shock myself by taking up all 50 minutes today. I never cease to amaze myself in terms of how much I can talk. I guess that's why I have the job I do. But be that as it may, we only have one more step in order to understand how individual nucleotides are put together in a polynucleotide. In other words, in an actual RNA or DNA strand. We're just one step away. The only thing we need to understand is that in between, let me make sure I have this in here. Polynucleotides and nucleic acids formed by, there we go, connecting the 3' OH of one nucleotide to the 5' OH of the next one. I don't want to be the guy that reads you the class notes. I just want to point out that I have that in your class notes. So yes, and we'll do examples. Oh, the 3' carbon is over here, or the 3' OH is over here. The 3' carbon would be here. This is the 5' carbon, and the 5' oxygen would be connected to it. But it starts over here. This is 1' over here. The 2' one is what determines if it's RNA or DNA. Yep. No, you're thinking about it exactly right. So, but the thing we need to get down is in between individual nucleotides, there's always a monophosphate ester from the 3' oxygen of one to the 5' oxygen of the next one. That's invariant. There's no exceptions. That's always the case. And we'll do a couple of examples of that. I think we'll fit in at least 2, and maybe even still end a few minutes early. We'll try. Good. So let's maybe draw a couple of dinucleotides. And it's just one of those things. It looks like this impossibly huge molecule. But I think already we can understand all of the parts that go into it. I'm just turning back to my nitrogen bases because I need them. So let's draw CG nucleotide, dinucleotide. of the type found in, wait a minute, let me see if I have an example question in the class notes, because I want to be sure that you get the answer to that. No. Nope. I don't know why there's an extra page over here. Probably doesn't really matter. Anyway, let me go back to my nitrogen bases, because I will need them. We'll draw a CG dinucleotide of the type found and just to make it official, put a triphosphate ester on the free 3' oxygen. Well, we already know it's of the type found in RNA, so we need to make sure we have both OHs in our ribose, or at least both oxygens. On the 3' oxygen, that means the free 5' oxygen is still going to be just OH. That's my free 5' oxygen. Then comes our ribose. And this is the 3' carbon and oxygen over here. So that's where we're going to make the connection. We'll leave this as OH since it's RNA type. And then up here, we'll put the cytosine. Where's my cytosine? NH2, double bond N, and then a carbonyl in between. So now here's where we put our monophosphate ester. Remember, between the 3' oxygen and of one and the 5' oxygen of the next, here's the next 5' oxygen. There's always a monophosphate ester. And that part is invariant. Let me circle that maybe in a different color. This monophosphate ester is always what you find between two consecutive nucleotides. That part is invariant, never changes. And then we have another ribose. That's where we're going to put our nitrogen base. We've got OH over here. The question says to put a triphosphate ester on the free 3' oxygen. So we'll put one there. And again, I'm only putting lone pairs in the oxygens that don't have a zero formal charge. There we go. And now I just need to put in the guanine. Where's my guanine? Whoops, not H, nitrogen. Now, of course, this wasn't a multiple choice question that I've just made, but one could imagine any number of multiple choice questions being asked about a structure like this, even without you having to memorize it. And I think that's it. Now, if it had said to put the triphosphate ester on the free 5' oxygen, then instead of OH, this would be O triphosphate over here. And this would just be OH over here. So, but always between any two nucleotide bases, always there will be exactly one phosphate ester, always. That part never changes. And actually, with only 4 minutes left, I don't know if I have the time to draw another one. That one is a mouthful. But again, as large as this molecule is, all of the parts are now things that we understand. We understand the nitrogen bases. Those are heterocycles we went over last week. We understand the ribose portion. And of course, if this were DNA type, then we would replace these OHs with Hs. And we understand mono and di and triphosphate esters. That's all we need to know in order to understand it. And in an actual DNA or RNA strand, this would just continue millions of times. But that same pattern, always with exactly one phosphate ester, between any two nucleotide bases. That's all there is to it. So you get exceedingly large molecules out of it, but all of the parts are now something we can understand. And that's how I'm going to approach also the other biochem chapters. Well, you've already sat through a lot of large structures, so I think you've done very well today. And I don't want to rush through a second one of these. So I'll leave that up so you guys can finish copying that down. And other than that, I guess we will start into lipids on Friday. Have a great day.